Okay, let me make a start. So this session is about our plans for education, and particularly global education reform, and particularly probably more discussing high school and college per se, although I think what we're talking about actually is reflected in both. But I think the sort of issues I want to cover are perhaps more prevalent as problems particularly in high schools than at least in some levels of college. So really I want to talk about several things. I want to talk about a vision for what's wrong, in particular with math. I want to talk about some of the progress we've made in executing to fix that vision and some of the plans we have but we haven't yet executed. The thing that strikes me and has struck me for a number of years now is kind of Wolfram's at the center of STEM education as nobody else. It's quite hard to find another organization on the planet that interacts, particularly with math, but you could say in more generality with STEM in as many ways as we do. And, you know, I mean, what I mean by that is, so we built computation stuff, as you know. We hire people who are technical. We interact with 10 million people around the world in different ways who are technical, which is a big fraction of sort of serious technical people at some level. In virtually every kind of sense connection with math, there we are, and that gives us a rather unique perspective on the story of math around the world, and the story of math in the real world. And I'm going to argue that, in fact, it gives us a broader perspective than pretty much anyone else on the planet from which to understand what to do. So the perspective we have, I think, is one that if we're not going to make some of the changes I'm talking about, nobody else will, or at least it's harder for them to get that vision, in which case, and also execute on some of these changes. The other thing, obviously, is we have our own technology to implement what I'm talking about in. Now, I separate these two because I don't think some of the things I'm talking about necessitate that we have to use our own technology, although, of course, we believe we've built the best technology to do that. So, but they are separate kinds of issues. Look, when I talk about the curriculum, particularly the math curriculum, I think there are two quite separate plans that operate in our organization, in a sense. And I think this is perfectly sensible and realistic. The obvious plan that most other organizations who are anywhere near this field have been operating is, how do we take today's curriculum and support it as well as we can? Right? So even if the curriculum is dumb in some way, how do we give the best tools, give the best support, improve the pedagogy, improve the delivery with all the things that we do? And that's a very rational thing, and we want to do that, and that's where you can immediately get results. And we have been, and many of you are involved in that and have been for many years with our software. The other thing which I've particularly been worrying about in the last few years, and much of this talk will be about, is how do we lead the replacement? And that's really what I wanted to focus on. And there are a lot of topics that come into both of these directions. There's coding, there's assessment, there's modern delivery, and there's what I'm going to talk about now, which is computer-based math, this idea of fundamentally changing the math curriculum. So let me spend a good fraction next time. What I was going to do is spend some time talking through this, and I hope leave a fair time for discussion and reflection on how we move forward. Let me start by saying one good thing, if you're into math. Math is high on the agenda around the world, right? As it never has been before. Right? More people fuss about math. I mean, governments, educators themselves, industry, everybody you think of, sort of all walks of life, are fussing about math. Mostly the fact that nobody can do it, or not enough people can do it, or the people who can do it can't do it well enough, or they can't apply it, or any of the associated problems. But in the end, most people realize that our economies are very dependent on technical people, and technical people, for their training, are very dependent on math. And it's not really working. Now, so the good news is math, the thing called math, is high on the agenda. The bad news is that I'm going to argue about 80% of it's the wrong subject. So we've got a thing that's called math that people are all excited about, which is great. The problem is what they're excited about is largely the wrong thing, I think. Although obtaining them over that way of thinking, I think, is not impossible. And in fact, there's a lot of it's confusion. So what am I talking about? Well, I think, actually, this suddenly went British on me. I guess I have maths versus maths here, because for some reason, when you cross the Atlantic, you lose the S. Whoops. You know, why that didn't activate. Oh, well, never mind. There we go. So, look, then we've gone back to American. Math in the real world, if you look at it, and what many of you guys do, is you take problems, you model them, you use the calculating of a computer, and you're trying to take the real world and use math to problem solve in the real world. In education, it looks pretty different. It typically looks something like this. You write stuff down, you look at endless problems that seem completely abstracted from anything you might actually do, and if you're very, very lucky, you can use a TI calculator. So this doesn't seem to match very well. So I'm going to argue that the fundamental problem with math education around the world that exists right now is, in the real world, most of the time, you're taking problems and you're solving them using whatever the best machinery is to do the computing of solving those problems. You're problem solving using the system of maths, but you're using a computer to do the calculating. In education, about 80% of the time is spent learning how to do the calculating by hand, in a sense, mimicking the computer. And that leaves about 20% for doing the real problem-solving methodology, and it also causes all sorts of other problems. And in a sense, that is the fundamental mismatch around the world that has happened over the last 50 years and is getting worse. And my argument is, unless you fix that, you aren't going to have maths that works. So let's dive into that a little bit more and talk about why that might be. Let's talk about why people learn maths in the first place. Or actually, a slightly different topic, which is why is maths one of these general subjects that everyone in the world is supposed to learn? There aren't many subjects in that category, right? There is most people's own language. I guess English, or maybe I should call it American if you're here. There is history. Most people have thought they should learn history of some sort. And there's kind of math. I mean, you can argue a few others, but basically it's in one of those very, very mainstream subjects. Now, I think there are, 3 reasons for everyone to learn math, if it's the right math. And the reasons are basically this. Technical jobs, which have so driven our economies in the last, certainly the last 50 years, but arguably much longer than that. What I call everyday living. The ability just to function in a modern world requires a much more quantitative approach than it did when we launched Mathematica, 27 years ago. And thirdly, what we might call logical mind training, the ability to think. Now, I mean, you can call this third one you can characterize in several ways, but basically the idea is there a structure that you understand in order to be able to think through problems, whether there are explicitly mathematical problems or not? If it's a business problem, do you have some way to hang off your reasoning? So those are 3 reasons I think it's good to learn the right math. Let's now talk about what is math. So I think math is basically a process of 4 steps. The first thing you're doing is you're defining a question. And the question may be rather fuzzy to start with. The question might be, if this room is sealed and we're all in here, how long can we live? Hopefully I'm not going to test that. The next thing is take that problem and turn it into abstract math. Right? So that's quite a hard step usually. So what that means is, why do you do this? The reason you do this is because abstraction allows you to have many, many different problems that have a very similar structure of sort of setup. And so what that means is if you've got those problems, we've spent hundreds of years designing mathematics to be able to take that problem, that question, and turn it into an answer if it's in that abstract form. So that's what gives you the power. The abstraction gives you a lot of the power, being able to take this fuzzy problem and turn it into an answer. So step 2 is translate it from the real world to math. Step 3 is compute the answer. Turn the question to the answer and in this abstract form. Step 4 is take the answer in the abstract form and go back to the real world. Did it answer the question? What's the number? How long can we all survive in here, right? It's a number we're looking for. And if the number comes out as -10, something was wrong. So that's kind of what you're doing pretty much in every math problem. Now, here's the problem. The problem is that this step 3. So in the current curriculum, step 3 is basically predominating with hand calculating. And yet that's a step that essentially nobody does above basic levels or around some edge cases. Nobody does by hand anymore in the real world. So why on earth are we doing that endlessly in education for most of the time people are getting educated? And what we should be doing is using computers for step 3 almost universally, and we should be using students for much more of step 1, 2, and 4. And in a nutshell, that is the problem with the world's math education. Another way to look at this is our CBM helix of math. And you can also think of going through these steps as going up a helix. And as you go up the helix, you go through these. But then when you get to the interpret step, it may be that you discover that actually, well, the interpretation means that you've got to go around and do the problem again until you refine it sufficiently to get to an answer that you think matches the kind of level of accuracy that you want. So that's kind of what you're doing in the math process. And by the way, we have a poster of this that is downstairs that tries to map this out that I'm hoping will get hung in more and more classrooms so people have some visualization of what they're actually doing. It's amazing that if you ask people in most classrooms, what are you doing in math? It's just a big fog, and including most teachers. So I'm arguing math is a much bigger subject than calculating. And STEM, obviously, by definition, is a broader subject than math. And if you confuse those two, you get into all sorts of difficulties. I mean, just to make this obvious for this crowd, but just to make this concrete, this is a standard linear simultaneous equation that you would learn at school and do by hand, no doubt. But as we all know, we can just change it and make something more complicated by making it a cubic. And the thing is, fundamentally what you're doing there, the concept of an equation is an important thing to understand. So the concept, the idea that you might have an equation, that might be a tool that you might use, is very important. But whether it happens to be linear, whether it happens to be cubic, is kind of to the side. It's a separate issue. And whether you happen to know how to solve a linear one but not a cubic one shouldn't be the main thing predominating in whether you use equations to solve problems or to try and make the problem linear when it really isn't linear because you couldn't solve the cubic because you had to do it by hand. And of course, one can make it even worse than this, right? Because if you do your Siri example, let me go back so I remember what I did, and say, solve x cubed plus 2 equals 2y, and y minus x equals 5, and Siri willing and everything else, we will hopefully get the answer, courtesy of, I'm going to show this on the screen here, courtesy of Wolfram Alpha, of course, through Siri. And let me just try and align this correctly, which for some reason my brain is not aligning the reflection. But, you've got to seriously ask, given that I've managed to do that by talking to my phone and solve a cubic simultaneous equation, if you take that equation and give it to most people after they've studied math for 12 years of their life, they won't be able to do it. So you've got to seriously ask why we're trying to train them for 12 years of their life to do something I can talk to my phone in 20 seconds and get done when they can't even achieve it after that time. There's obviously a problem there. And it's funny because I've done that demo for actually groups of ministers of education things around the world, and they're all like, oh yes, you've got a point. We never thought about that before. So another thing I want to talk about is when we think about the curriculum right now, it's labeled by, in a sense, the mechanics of what's inside. This seems a dumb way to label something. If you label how you drive your car, for example, by, well, it's kind of like you drive your car by knowing how the seats are made. It doesn't seem to match. And to some extent, labeling things by, inverting matrices or simplifying surds, which I particularly hated, or whatever, doesn't seem the right way to sort of head your curriculum. What you should be doing, in my view, is heading it with problems that invoke all sorts of different bits of math, because in the end, that's what you're going to have to do in life. So, design a currency. What coins and notes do you need? By how many levels of friends you separated by on Facebook? What, making a perfect password for your login, the problem of every 6-year-old today. Stop their friends nicking their account. What's a beautiful shape? That's a perfectly relevant mathematical question. The Greeks considered it. Why shouldn't we? And, things which, of course, you can ask but couldn't ever imagine doing in the old world. By how much can you compress a photo or video or music before you notice? Again, a problem that we all have. I mean, should you save the 256K edition of your music, or should you save some different edition? Should you compress your photos? But, you can actually, of course, start playing with these things and figuring out what it is, what these things mean in reality, what changing the algorithm actually does in different cases, and so forth. These are real maths questions of today. So my argument about what we're trying to do with CBM, so-called, is, in a sense, this is the, I guess this is the logic. You know, if math is for all students, so if you're assuming, if you're going to argue that math is a general purpose subject and not some niche subject like ancient Greek, then that implies that math in education has to more or less match math in the real world. And which implies that math in education should be the kind of math I'm talking about. I mean, that's basically pretty much as bold as that. You know, there are various mathematicians who argue to me, oh, no, but there's this long history of math and blah, blah, blah. The problem with that is, in the end, if it's only relevant to 1% of the population, that's great. It's great if people want to go study that subject. It's a good subject, just like ancient Greek is a good subject. Problem is, you can't justify it for everyone. It doesn't make any sense. And I'm going to argue that today's math is also largely a proxy for math. So what do I mean by that? Well, it's a bit like Latin. I guess in the US you didn't typically learn Latin. In Britain I learned Latin, actually. But Latin is sort of degenerated in terms of well, I guess it's the same as it was 1,000 years ago or something, but it's degenerate in terms of one's level at which one learns it. Now, it may be, I mean, I think the reason I was taught Latin, though I never discovered in 10 years, I think the reason I was taught Latin was so I learnt English grammar. At least that was one reason. It may be that learning English grammar by learning Latin is a perfectly reasonable thing to do. Maybe that's a better way of teaching me English grammar than just learning English grammar. But it does seem to me that your starting point ought to be, if the end result you want is to learn English grammar, then that's probably the starting assumption you should use, that you should teach English grammar, right? Similarly, if you want to learn real math, it seems to me that you should start from the idea that let's mimic the math in the real world and take that into the classroom and use the real math to learn, rather than some proxy that apparently may have existed 50 years ago, but actually doesn't get used in the same way and is some really quite different subject. So that's an argument I've found. You've got to learn how to do your quadratic equation by hand if you want to learn how to problem solve with math. You've got to learn Latin if you want to learn English grammar. Maybe. I don't really buy it. And in fact, I would buy it more for Latin, frankly, than I do for our existing math curriculum. Another thing I wanted to also contrast is math versus coding. Coding has become a sort of in thing, starting, I think, in Estonia, moving to the UK, and now here, and percolating out to various other countries. For some reason, the English-speaking thing first. I don't quite understand why. Maybe because all the languages have words that are typically in English. I don't know. I do think coding is important, but for a different reason from most governments. Most governments think coding is good because people make apps, and they haven't quite got further than understanding why that is. I think the reason coding is important is because it's the way you write down math. If you have a technical idea in the modern world, the way you write it down is to write code, realistically. Now, in the olden world, one way you wrote this down was to write mathematical abstraction. You wrote algebra, algebraic expressions. And you can still do that. The problem with that is it's sort of only a partial, there are only certain things you can abstract to expressions. The much more general thing you can do is to abstract to code, because code covers all sorts of cases that expressions don't cover. And in practice, that's what you do, right? Because you want a computer to run it. So I would argue the reason code is crucial is so you can write down technical ideas. And it's, in a sense, the equivalent of handwriting as it was to English. In the olden world, handwriting was crucial because there's no other way to write your ideas down. And you learnt it in English, when you were at school, in primary school. Even though you used it in history and math and everything else. I think coding actually should be part of the primary math curriculum because I think it's sort of the same relationship. So in a sense, the way I think about it is math is a system of problem solving, a system of doing STEM and life. Coding is a way to express math. And of course, particularly, we have our Wolfram language, which I think is highly expressive and has math built into it. So that kind of links the two in a very, very nice way that hasn't really been done before. Now, here's a point I like to make to people. If you remove the computer, you remove the context. And this is a point that I think is perhaps the most crucial point about this argument that is completely missed by curriculum-setting authorities. So the key point is here that, the reason math is so important in the real world today is because it's applied in so many disparate areas, represented many of them at this conference. It's applied in biology. It's applied in mass data in all sorts of places. It is also applied in traditional places like physics. It's applied in art. It's applied in ophthalmology. I'm watching back there. It's applied in all these places. That was not true 50 plus years ago. It didn't get applied in many of these areas because it didn't work. The reality of it is math didn't work very well in anywhere that needed mass computation, like anything that required data, for example. It just didn't work because there wasn't mechanized computing. Mechanized computing has allowed math to be applied in so many places. So the very thing that has made governments panic about math, because the reason math is so important to governments and others around the world is because it's so applicable to so many things, which is driving economies and jobs and people's lives and so forth. So that very reason why it's become so important in the real world is being locked out of education, because we're telling people you are not allowed to use computers to do the computation. And so my argument here is if you remove the computer from maths education, you are removing almost all of the real context. You can't do real biology problems in math, in education, if you don't have a computer. Mathematically, you can't do them because you have mass data. It doesn't make any sense. You can do it with 10 data points, but that's different. So by removing the computer, you remove the context, and people see through this. Students and teachers all understand that the problems they're being given are basically don't make any sense because they're not real. They're not real because they can't do mass computation. There are things you can change in reordering the curriculum. So here's a very simple example. Why don't we teach thermodynamics at primary school? The basic idea of thermodynamics, is fairly simple. The more atoms you've got in a box, basically, other things being equal, the higher the pressure, right? If you change the container to a smaller container, the pressure goes up, et cetera, et cetera. There are all sorts of things you can play. But the basic ideas here, the feel you can get, is something that I think comes fairly naturally. Here's another thing. This comes from some Estonia modules I'll talk about in a bit. This was a nice example we have where we split the class in two. And the idea is that some of them toss coins, actually do 200 coin tosses and note down their results. And the other half cheat by just typing in heads and tails to the computer. Right? And the question is, can the teacher tell who's cheated and who actually did the experiment? And the answer is yes, typically. So my cheat here, you'll see that I only passed one of the 5 tests on this set of data. And so I pretty much concluded that I cheated. And the kids are absolutely amazed by this, right? It's like, how can the teacher tell who cheated and who didn't cheat? And actually, just to show you this, if I can get this right, I could guess do something like, I guess I could, let me semi-not cheat. So I'm going to generate 200, coin tosses. But because we're using our nice random number generator, I guess I don't, I don't know whether this is cheating or not, but let me paste that into here. It's zeros and ones instead of heads and tails, but I think it'll cope. And you'll see here that, in fact, that case passed all 5 tests. So that's sort of what would have happened if they'd done the coin toss, really, except I semi-cheated. So this leads into fraud detection, right? I mean, this is the basic idea. You're looking for patterns in data. Can you figure out whether the pattern's real or not real, whether it's a cheat or not a cheat, et cetera, et cetera, et cetera? This is a powerful thing. But it's actually quite amenable at a young age. So you can reorder the curriculum if you think this way. Now, just to be very clear, what I'm talking about right now is computer-based, not computer-assisted. So what do I mean? Computer-based means take the real subject, apply a computer in education just as you would in the real subject to actually do the calculating. What I mean by computer-assisted is what mostly has happened around the world, which is take the computer and use it as a pedagogical aid or replacement even for the teacher in some way that works with the traditional subject. Or maybe not. I mean, I'm not saying you can't multiply these two together. I think you need computer-assisted to deliver computer-based. But computer-assisted, I mean the delivery. But it's no good delivering the wrong subject. That's the point. And it's kind of like, however well you deliver the wrong subject, it's not going to be the right subject. And you've got to get the subject right before you figure out how to deliver it. And I'm all for using computers to improve the delivery. There's nothing wrong with that, if they really do. OK, so that's the thesis. What are we doing to make the change? How far have we got? So the first thing I'm just going to emphasize is vision for the right subject. It is amazing how little vision there has been in math education for years. I mean, Seymour Papert and others had a vision. But a lot of the problem is that everybody wants to try and reform math education, tries to think too much about the next semester. They're so worried about getting the thing to start that they lose the vision. And so everybody loses the vision. And maybe they didn't have a clear vision to start with. So one thing I think is very important is one keeps the vision, even if it will take years to implement. Another thing is to build the right subject. So one of the things we've been trying to work on is what are the outcomes we actually explicitly want from math? So this is a 10-dimensional list of outcomes. Again, you go around the world and you ask countries and everybody else, what do you want to achieve from 12 years of teaching everyone math? And they don't know. I mean, they claim they know, but it doesn't add up. What they typically tell you is, we want critical thinking skills. And so that's great, but what does it mean? And at another level, they say, we want people to know how to put ticks on bar charts. And it's like, well, okay, maybe that's a useful skill, maybe it isn't, but it's somewhere deep in the trenches, with the rats running around. It's sort of deep down there. So what we try to do is construct a 10-dimensional list of sort of the outcome dimensions. And it's an interesting list, I think. It's confidence to tackle new problems, which involves practical things you can do. Knowing how to read documentation of math, for example. Knowing how to teach yourself new tools. These are practical things you really need. Abstracting to mathematical concepts, that's perhaps a more traditional one. Planning and managing the process. Most people leave school, not having the foggiest idea how they're going to take the math they learned and actually using it on a real problem. It seems to me it's a crucial thing. It's like going into management and telling you that you read all these books, but you're never going to talk to an employee ever. And before you get in to manage anybody, you're never allowed to do that. And then you go in on day one and you've got to manage a large company, and it's just going to fail, right? It's got to fail because it's complicated. Stuff comes up which you don't expect. Things don't react like you were told they would. People don't react that way. So those are all important things. Interpreting, critiquing, verifying, generalizing models, communicating, collaborating, those are perhaps more obvious. This is an interesting one. So the idea of an equation or a matrix, the concept of the equation or the matrix, isn't the same thing as the detailed equation solving or inverting of the matrix. Right? One is a concept of a tool, and the other one is the actual tool itself and how you use it. And if you don't separate those, you get into a big... People say, I want in a maths curriculum, I want people to learn the quadratic. Well, what do they mean? Do they mean the idea of an equation and how you'd set it up and when you'd set it up and how you'd use it? Or do they mean, given that you've set the equation up, the actual detailed mechanics you'd use to solve it? They're different. And it's often the former is totally left out of that. And that's crucial because if you don't understand when you'd use an equation, when you'd fit a curve, if you don't understand those things, it's not a lot of use to you. And instinctive field math. So those are some of the things we worked on for building the right subject. And it's very complicated. Which bits of math? What's the layering? What's the narrative around it? So another thing that needs to be done is to align, this is this is probably the outer core of this problem. Clearly assessment drives a lot of what happens around the world. And the assessment is pretty goofy, much of it, and is driving people to do the wrong kind of math. And so over time, a key thing of making the change is to start aligning the assessment, which is to start to win the vision argument. But that's a slow burn for traditional assessments. But I want to come back to non-traditional assessments, which are growing in currency. Certainly in the UK, for example, the traditional governmental-backed things are becoming fairly degenerate in many respects, to the point where people are looking for other kinds of ways to say, I'm good at this job, because the traditional A-levels, as we call them in the UK, for example, don't particularly do that job very well. It's like when we hire people, it's like, really, what they did in their A-levels doesn't tell us a hell of a lot about whether they're going to be good at the job, frankly. And I think that's true in many countries. The things have got disconnected. Another problem is math marketing. So, again, back in the UK, because I know the example where the government was very proud of saying that, long division, they were going to make everyone learn how to do long division now, and properly. Now, apart from being damn stupid to start with, because it's unnecessary, it's also damn bad marketing. It's what you're telling students that the best thing, the most exciting thing they're going to do in their whole maths curriculum is learn some blasted process that the computer should be doing anyway. It doesn't seem like a great sell. So one of the things we've got to make sure is that we actually make math seem cool and seem interesting. And you probably know our ComputerBased Maths website, where we've been trying to make the case and make some of these things out. But I think there are various things to do along that. So making the case mesh with today's ed environment. The fact of the matter is there's a huge infrastructure of math around the world, and the question is, how do you mesh with that? There's teachers, there's technology, and there's setup. And so I think there are rather good ways, and not as discrepant ways you might think, to mesh with these things. And kind of like that's another part of what we need to do. So what's the progress so far? Well, we founded computerbasedmath.org a few years ago, and its aim is to build a new math curriculum and to make sure that we get that deployed in as many places as possible. What's the progress? And also to make the case. I mean, good piece of progress, I think, is the discourse is starting to change. Slowly but surely. There is starting to be a change. People are starting to say, and I've seen articles in the New York Times, I've seen articles, there's certainly plenty of things in the UK, things in other countries saying, you know what, maybe we need to look at the subject of math. Maybe it's not this sort of God-given subject that arrived one day and that should never be touched. Maybe there's a problem, and maybe the problem is actually quite severe. So that is coming through, and that is percolating. Other progress is we really did start to build a curriculum. This is slow going, but I think we've made quite significant progress. And the progress is several-fold. One of the pieces of progress that's actually hardest is sort of the frameworks. What I would call the frameworks, the intellectual and practical frameworks. So what do I mean by that? Well, if you're delivering a new subject which nobody's ever seen before, what do you do to manifest that? How do you think about it? How do you structure it? So we've structured it into things called activities, chapters, topics, modules, and modalities. And roughly speaking, activities are sort of in a sense, the atomic, not exactly the atomic, but the normal sort of currency unit. What they are is, here's something you want to do. It's inside a storyline that's a module, and that's broken up into chapters, and there are certain topics you need to cover, and then there are things called modalities. And what we mean by modalities are, in a sense, the delivery mode. What is it? How are you delivering that piece of the activity? What do you actually have to do? Is it that your teacher is lecturing you? Hopefully not in most cases. Is it that you're swapping data with your teacher? Is it that you are interacting, writing a program? Is that the modality? So that's kind of what we mean by modalities. And as some of you know, we got our first country excited about computer-based maths, and that is Estonia. And so about last year, we've been building, they wanted us to redo their high school probability and statistics curriculum. And so we built that. And we had our first pilot that ran in the last few months, and I think was really pretty successful across about 10% of the Estonian schools. Lots of stuff to learn, lots of stuff to fix, but the overriding thing I found out of that was that, the teachers, the biggest concern, particularly the government had, was that the teachers wouldn't manage it. They actually had less concern that the kids wouldn't manage it, I have to say. They were more concerned about the teachers. The reaction of the teachers, was a lot of nervousness, but actually they found it easier than they thought to some level, because they could actually understand what the point was of what they were doing, and so could the kids. And the kids had more fun doing it. And the kids actually came out saying they thought it was easier than some of their traditional math. But I think it's a lot harder. I think if you look at the topics, they're university-level topics, some of them. So let me just try and fire up, just to give you a rough flavor of this. And John will talk a bit more later about the actual insides of this. So this is what starting computer-based math in Estonia looks like, except there's an Estonian version, but I won't go into that. This is the English version. So we've got a bunch of modules here. These are the module headings, and there are 9, I think, how many modules are there? There are 12 modules, I think. And the first module is entitled, Am I Normal? So the problem for the kids is to figure out, am I normal? What does that mean? What is the mathematics of am I normal? And so you open up a module like this, and this is the teacher view of it. So one of the things we've ended up doing is building a whole bunch of infrastructure, teachers, students sharing, what do we actually deliver? So this is a lesson plan for the teacher, and this is sort of what you're going to cover in the lesson. Doesn't look terribly exciting, but we start off, and everything in blue here is only for the teacher. This only appears in the teacher version. And so here we're talking about what does normal, what are good ways to think about, is it height, is it foot length, is it what you wear, is that normal? How are we going to quantify this? And we go through various types of activities here, some of which are swapped centrally in the classroom, some of which are not, and I'm not actually going to do them here, but you can see that this is the sort of mode in which this operates. And further down, you can, then we're trying to get them to look at charts and to pick out interesting things from the charts. So, okay, so when you look at a standard chart of things, what do you count as being normal or not? What's interesting about the chart? These are fuzzy questions. So this is just one example of sort of a module. Just a few of the others here. Proof by survey. How can I convince you? So the point of how can I convince you is to get people to look at data they're given and to teach them the ways that data will be gamed on them. So the fact is, when you see a graph on the news website, it's going to have it may have a bunch of tricks or skewing or whatever in it. The question is, can they learn this? So the idea was get them to understand how people do this stuff so that they're not fooled by it. So here's an example, just a simple example. These are mobile phone sales data from Estonia in the 4 quarters of 2012. And you'll note quarter 4 is actually slightly smaller in sales than quarter 3. The question is, if you're the sales manager, how would you present this graph so that it didn't seem like that was what was happening? So, a standard problem. Now, the thing is not to get folks to understand that they should cheat all the time, but the fact is these are going to be pulled on them. If they're managing the sales manager, this is something that will happen. And so maybe I'll make it 3D and I'll have this piece closer to me. And actually that already looks like the 4th quarter here was a little bit more promising than the 3rd quarter and so forth. So that's a very simple example, but that's the sort of thing that we want them to understand, because if they understand that, it'll be easier. So the student version is quite nice because it kind of immediately syncs with the teacher version, and you can go full screen and so forth. So anyway, that's a rough guide to some of the things that we have been starting to do in Estonia. And we're also starting things in Sweden and in African universities. So what have we got to do? Well, we've got to do the rest of the math curriculum. I think it's probably about 10%. And we've got a lot more to do, although we've done more activities. And you might ask how it's broken down. My argument would be it's something like geometry, signal processing, though we need a better name for that, sort of modeling, and architecture of maths. There's some other elements, as well as what I would call this, which is data science. Also to do is to consumerize. Right now we're setting this up for classrooms and governments and all these things. But actually, we would like to be able to just deliver this to individual parents and teachers. We just aren't ready yet. It's too open-ended. We haven't quite got there. I don't think it's easy enough to understand at this stage. The other big question which I have is, should we be going into the assessment market? A zillion people have told me, you guys should start running math assessments. Why? It seemed just crazy to me, okay? Why are people saying this? They're saying, well, because people might believe that math assessment that Wolfram ran was worth something and was the right thing. So I don't know. I'd be interested in your views on whether that's a useful direction for us. I mean, one of the things I want to do is establish assessment that actually makes some sense. And also to do is sort of coding education. Now, coding, as I said, is a prerequisite. And we have been working a bit on that in coding and the programming lab. And Adriana was just going to just explain the programming lab that we've been working on and give you a quick demo of that.
Hi, everyone. Can you hear me okay? Good. So like Conrad said, my name is Adriana O'Brien. I'm working with the team developing the Wolfram Programming Lab. And you saw a brief view of this earlier in the keynote. What the Wolfram Programming Lab is really focused on making a safe environment for learners, where not only do they get access to the Wolfram language, but they also get access to these activities. These activities are called explorations, and they're interdisciplinary, so you can get computation across all subject areas. So here's one called word ladders. And as you can see, we've got a brief narrative up top to walk the students or the learners through either a particular problem or a question or anything like that. But then down below, we've got this code zone. And what this code zone is really a way to engage the learner in, like I said, either exploring a new function or answering a different type of question. So here then it says, get the list of words that have certain patterns. So now instead of starting with Z, I'm going to start with A. And there we go. And it walks walks me through how I would answer this type of question or how I would answer this type of scenario. So that's basically an overview of the programming lab. If you'd like to know more information about it or have any questions.
It's a little bit like, it's not CBM exactly, but it's the same essence, right? It's sort of like you need to stop worrying about the calculating. You've automated out of that. And one thing to think about math for 25 years, what is going to happen in the current scenario? I think there are basically three outcomes. Math will be run out of business by a new subject, which you can argue is what I'm trying to do somewhat, except I would call it math, but you could have it, math as the traditional subject in schools, can't exist in its current form. It will fail. It is failing. I mean, it's just, there's no way around that. The question is, will it get reformed inside the subject, or will it be supplanted by some other subject? Now, classics ran out of business. People don't do classics anymore. There was a time in the 19th and early 20th century where people just couldn't believe that you would not have a major subject in schools of being classics. But it did slowly die and is now largely dead. It's a niche subject. The same will happen to math unless it gets reformed. And the cool thing is, the people who reform first to this new kind of math, it's a bit like having a sort of microcosm of universal education that the British in particular had early. Having universal education, whenever you do it, is been a good thing, I think most people would agree. Having it being first or being very early with it gives you a real boost. And I think Estonia, for example, have understood that point, and others will slowly follow. Why now? I think it's important to understand there's huge emphasis around the world for this change, for a change. People don't really know what they need to change to. They know what they're doing is wrong. And there's ubiquity of devices, and we have decent interfaces to this. The other way to think about it, Stephen mentioned this morning automation, which has been a thing I've pushed for many years as being our core strength. The real point now is, in a sense, we and other people have automated computation. Right? So mechanized maybe would be a better word. 19th century people mechanized, factories got mechanized. Physical machines could do things people did physically. Now we have machines that have done a fantastic job in automating calculating. And so the question is, what do you do in education when you've got something that got automated, which you were learning as part of your education? What do you do with it? Well, there are two ways you can handle it. You can say, well, you need to learn it first before you use the machine. Or, given that the machine is now there and working, we need to learn something more, different. We need to stand on the power of automation, in this case, and go further. And that's what I'm arguing for STEM, and that's what I think we have the ability to deliver. So the summary is 4 things, I think. Change the world's math curriculum is one of our visions and practices and plans. Offer the best support for today's STEM curriculum. Have coding be a follow-on. Have the Wolfram language be the follow-on to Scratch in education. That'll be a great thing to do, and I know we have a lot of support from the Scratch folks, like the guy who started Scratch, Mitch Resnick, and others, are very supportive of the idea of, at some point Scratch, which a lot of people are using at an early stage, kind of runs out of steam. And the question is, where do you go then? Do you go and use Python? That seems like a crazy thing to go and do. I think we have a very nice place to be there, sort of secondary school, where people can jump from Scratch into a sort of Wolfram language thing, and then also mix the math with the coding. And whether we should do Wolfram assessment. Thanks very much.